Imagine a remote forest station with limited power and no internet, where detecting acoustic events like bird calls or animal activity is crucial. In such a scenario, you need an embedded system that can operate autonomously, detect acoustic events, log data with accurate timestamps, and consume minimal power. That's exactly what this demo will showcase. A low-power acoustic detection and data logging system using Microchip's PIC32CM GV Curiosity Nano+Touch evaluation kit. This demo includes the PIC32CM GV kit mounted on the Explorer board, which provides easy access to onboard peripherals and streamlined prototyping. The Explorer board expands the functionality with key components like a MEMS microphone, SPI EEPROM for data storage, touch button interface, and power monitoring capability via the PIC1944. Together, this compact yet powerful setup allows developers to demonstrate real-time acoustic sensing, efficient data logging, and ultra-low power operation, all within a self-contained development platform suitable for proof-of-concept designs. To set up this demo, the hardware required includes the 32-bit ARM Cortex-M0 Plus based PIC32CM GV Curiosity Nano+Touch evaluation kit with clock speed up to 48 MHz mounted on the Curiosity Nano Explorer board. The Explorer board hosts the microphone, SPI EEPROM, and PIC1944 power monitor for current measurement. To flash and debug the firmware, connect the PIC32CM GV board to your PC using a Type-C USB cable. Ensure the jumper wires are connected properly between the kit and the Curiosity Explorer board as shown on the screen. For more details, refer to the online documentation for this demo. Download the MPLAB Harmony v3 repositories and install the required software shown here. You can use MCC Content Manager to clone these Harmony packages. Serial monitoring can be performed using application like TerraTerm, and current profiling can be carried out using the PIC194X demo app. If you are new to MCC, check out the video in the description for more information. This application is designed to operate in two functional modes: acoustic detection with data logging and low power monitoring. Upon reset, the system awaits the user to manually set the RTC time and date over a serial terminal. Once that is done, pressing the onboard touch button transitions the system into data log mode. In this mode, the LED is turned on and the microphone connected via the Curiosity Nano Explorer board continuously listens for acoustic events. When a sound is detected, the system records the timestamp using the RTC and logs it into the SPI EEPROM. The data is then read back and printed on the serial terminal via UART for user inspection. Pressing the touch button on the kit again moves the device into low power standby sleep mode. The LED turns off. Non-essential peripherals are disabled. Clock sources are switched to low-frequency oscillators. The device waits in the state and wakes up only on an interrupt, demonstrating the power efficiency of the PIC32CM GV microcontroller. To achieve this, we will download the project from the kit page, open the project and launch the MCC, check the peripheral configurations in the MCC, compile the project and see the output. Navigate to the kit page and download the project as shown here. Extract the downloaded file and open the project using the MPLAB IDE. Right-click on the project and set it as the main project. Next, launch the MPLAB code configurator to view the pre-configured peripherals. The real-time clock RTC provides accurate timestamping. SERCOM5 is set up as SPI master for EEPROM communication. The SERCOM2 is configured for UART communication with the serial terminal. The analog comparator AC handles analog sound detection. TC0 manages timing operations. The SysTick provides periodic interrupts. And the peripheral touch controller PTC detects capacitive touch button presses for power state control. The clock system is optimized for low power operation. The DFLL runs at 48 MHz for core functions and high-speed peripherals like SERCOM2 and SERCOM5 via GCLK0. GCLK1 is sourced from the ultra-low power oscillator at 1024 kHz, while the others use the external oscillator at 32.768 kHz. System control DFLL TC0 even system, and AC operate at 1024 Hz via GCLK1. The PTC runs at 32768 Hz via GCLK2, and high-speed communications remain at 48 MHz via the GCLK0. You can always go to the project files and check how the code is implemented. You can always refer the MCC to modify the existing peripherals or add new peripherals to your application. To build and flash the firmware, click on the Make and Program Device button on the MPLAB IDE. Ensure your connected hardware tool is recognized as PIC32CM GV device. The programming will take a few seconds, after which the application is ready to run. Now open the serial terminal and configure it to the baud rate as shown. Reset the board using the C Nano Reset button on the Curiosity Explorer board. The terminal will prompt you to enter the date and time in the format as shown. This sets the initial time for RTC logging. Once RTC is set, press the touch button on the PIC32CM GV board to enter the data log mode. The LED will turn on and the microphone begins monitoring the environment for acoustic events. Any detected event is logged in real time with a timestamp to the SPI EEPROM. These logs are then retrieved and displayed on the terminal window over the UART. To enter low power standby sleep mode, press the touch button again. The LED turns off and the system transitions into a low power sleep mode. All unnecessary peripherals are shut down and the clock frequency is significantly reduced. To observe this power efficiency in action, you can connect the system to the PIC1944 power monitor through the CH1 channel on the Explorer board. Ensure that the following jumper settings are performed for power measurement. Open the PIC194X demo app on your PC. Ensure that the board is connected and set the average sample value to 20. Start acquisition and observe the current average in milliamperes. During standby mode, you will notice that the current consumption is as low as microamperes, showing the low power strengths of the PIC32CM GV microcontroller. Explore more demos and projects for the PIC32CM GV MCUs and the Curiosity Nano Explorer board by visiting the MPLAB Discover page. Visit microchip.com/harmony to learn more about MPLAB Harmony v3 features, documentation and tutorials. We hope you enjoyed this brief demonstration. Thanks for watching.